pleasure. I have some good news, bad news, and a confession. So I'll start with the bad news. I did not bring a power cord for my laptop. But the good news is that means I'll keep my time and make the talk reasonable length. Confession is that I am also an amateur astronomer, and I have been since I was about 8. I grew up in Belgium, hence the strange name. I'm a Dutch speaker, even though my name is French. My passion was always looking at things that are changing in the sky. So satellites and meteors were my passion back when I was a teenager and a nerd. I'm still a nerd, but by some miracle I've been able to make a career out of this, and I'm studying an object that as an amateur astronomer I always thought was the most boring object to look at. And I apologize to any solar observers here in the crowd. I've obviously changed my mind since then. I'm studying the physics of the sun, and the sun of course is our nearest star. As you can see from my byline, I work for the Lockheed Martin Solar and Astrophysics Lab. We actually have a lab in Palo Alto. We are mostly working as a contractor for NASA and NOAA. But there is a reason why Lockheed Martin was historically interested in this and why they even have a solar and astrophysics lab, and I'll come back to that as I go through my talk. So what you're seeing here in the background is ultraviolet light, and I'll come back to that in a minute too, of the sun. You're seeing an image here of a coronal mass ejection, which I'll come back to as well. It's a big eruption on the sun that is where gas is ejected from the sun's surface or atmosphere into outer space. You can see here the Earth for scale. So we are pretty insignificant, as you can see, and I have more movies to show that. The black line that is nervously moving back and forth is where we can capture the light in more detail, and I'll come back to that too. It's where we do spectroscopy. So in my talk today, I'm going to talk a lot about data taken with a variety of instruments. One of them is on the ground. It's a Swedish solar telescope in the upper left. It's in the Canary Islands. Their weather wasn't very good, and they moved to somewhere more sunny. We have some data from that telescope in this talk. And then the other 3 satellites are satellites that orbit the Earth and that are focused on the sun and studying the sun. The sun is the nearest star, and so it gives us a chance to really study processes in detail in a way that we can't do anywhere else in the universe. So we're going to be looking at a lot of data from the Solar Dynamics Observatory, which we at Lockheed in Palo Alto built this instrument called the Atmospheric Imaging Assembly, which you can see here, our telescopes looking at the sun. The Interface Region Imaging Spectrograph. I'm the principal investigator for this satellite. It's been looking at the sun since 2013. SDO, Solar Dynamics Observatory, since 2010. And well, I'm also going to show a little bit of data from the Hinode satellite, which is a Japanese satellite in collaboration with NASA and the European Space Agency. And I'll talk, at the end of my talk, I'll talk a little bit about a new mission that we're developing for NASA right now. So, but maybe I'll start very briefly with an introduction to what kind of light we're looking at and describe a little bit the different types of light and which lights that we're using to study the sun. So obviously we're very familiar with the visible light. Light is a wave phenomenon, has a wavelength. You can see that here in meters what the wavelength is. They're all very tiny. They're on the scale of protozoans here in the visible light. And so of course we have the rainbow of colors that we get in the light, but we often use light at different wavelengths to study the sun. And the reason for that is that it is emitted in different layers of the sun's atmosphere and allows us access to phenomena that we can't see with the naked eye. So the visible light, of course, we know very well. It can penetrate the Earth's atmosphere, which is very good for us, because it allows plants to grow and it gives us food and energy. There's other types of light that does not make it through the Earth's atmosphere, which is very fortunate for us. Gamma rays, X-rays, ultraviolet light, most of that, well, none of this makes it through to the Earth's surface. Some of the ultraviolet light did and gives us tans or sunburns. And of course there's also infrared, microwave, and radio light. And we have different detectors for all of these different wavelengths and all these different types of lights. Much of what I'll talk about today will be based on either visible light or ultraviolet light or even X-ray light. So the reason why I never thought the sun was very interesting as an amateur astronomer is because with the instrumentations that I had back in the 80s as a teenager in Belgium, all I really got to see was this. And mostly the amateur astronomers were just counting spots, so I was never really that interested in it. There is fortunately a lot more of interest once you start zooming in on the sun in more detail. You see the sunspots, obviously, but as you start getting to a more and more of a close-up view, you start seeing some very fascinating physics phenomena. And in particular here, what we're seeing are actually convection cells. The sun is a ball of gas, but it has, just like when you boil water on a stove, energy is transported from the hot plate of the stove at the bottom to the surface of the water through convection, through mass motion. Mass gets heated, becomes less dense than its environment, starts to rise, is buoyant, gets to the surface, radiates its energy away, and then cools back off and forms a cycle. And you can see that cycle here in a movie that was taken from the Swedish Solar Telescope. And I'm sure that many of you have seen similar movies taken also with ground-based telescopes. This is one of the best telescopes in the world. It has a spatial resolution, allows us to resolve small details as small as of order a couple of tens of kilometers in the sun's atmosphere. Now the sun is 150 million kilometers away, and so seeing those small details really requires very high quality optics. And a lot of the challenges observing from the ground is that the Earth's atmosphere, when it gets warm, starts to make things fuzzy. This is being corrected for here in this data. You can see some of the artifacts from the correction at times through the use of adaptive optics, through mirrors that are deformed as they try to correct for the deformations that the Earth's atmosphere brings into the wave of light that comes into our telescope. Now, what do we see in this? We see these convective bubbles. These are kind of like the bubbles that you see in boiling water. And then these dark lanes is where the gas cools off and becomes denser, then its environment starts to sink again. Now the other really interesting thing you see here is this crinkly stuff. Kind of in the dark lanes, you see all these bright little, we call them filigree, I'm sure that's a term that some of you are familiar with. Those are concentrations of magnetic field. The sun's magnetic field behaves in a very different way from that of the Earth. The Earth, as we know, has a North Pole and a South Pole. The sun has many North and South poles, and you can see them here illustrated as white being the North Pole and black being the South Pole. You see the clock racing here. This is about a couple of days of life of the light of the sun. You can see how fast the field evolves and how dynamic it is. And in particular, so the scales here, this orange circle is about the diameter of the Earth, a little bit less than that. This is a couple of Earths, and then this is about, I guess, the size of California. And so you can see how magnetic field is jostled around, essentially by these convective motions, by these motions of the gas. And it's the interaction between the sun's magnetic field and the convective motions that really drives a lot of what we see in the sun's atmosphere. In particular, the magnetic field is kind of a slave to these motions, these convective motions at the surface of the sun, which we'll talk about later. But as you go higher into the atmosphere and the gas gets less dense, the magnetic field becomes bossy and starts to dominate and starts to fill the whole volume. And it kind of forms these kind of wine glass shaped features here where the field is very concentrated at the foot points, but as it goes into the atmosphere, it starts to expand. Now, when you have these foot points being jostled around, like this random motion here, just like you have with a real wine glass, all kinds of things can happen. If you slash wine glasses together, you break them, and there's a lot of mess going on, and that's a lot of what happens in the sun's atmosphere. It's the convection motions and the impact on the magnetic field and the resulting heating that comes from it and dynamics that come from it that drive a lot of what we see in the sun's atmosphere. So just for scale, we see the sun here. We see the sun's atmosphere, actually. It's a couple of millions of degrees. But we also see one other object in here, and it's this one here, and that's the Earth for scale. So you can see that we are very, very insignificant. The sun has many different layers, and you can see that in this movie here. We're kind of taking a peel, peeling the onion here, looking inside of the sun. The core of the sun is where energy is generated. There's such enormous pressure there that atoms are smashed together and fuse, and that releases a lot of energy in the form of radiation. And you can see that's that yellow region here. About 70% of the way out, the gas is too opaque and doesn't allow the radiation to go through, and actually this region here becomes convectively unstable. So energy is no longer transported through radiation, but is actually transported through mass motions. And we'll see some of that here as we get closer and closer into the sun. We start seeing the convective motions and the interaction with the radiation. As you can see here, these are like the convection bubbles that we saw also on the surface. They're also in the interior. And all of that is driven by the fact that all of the energy is released at the core, gets transported outwards, and sets up two zones, a radiative zone, a convection zone, and then the surface. The surface looks like a real solid surface. It isn't, of course. It's just gas, but it's where most of the light escapes, and that's why it looks like a very sharply defined boundary. And so here are these zones that I talked about, the core all the way in the middle where the fusion happens, the nuclear fusion, the radiative zone, then here's the convection zone. There's a lot of flows in the interior of the sun. That's not something I'm going to talk about too much. We know a lot about this by looking at the surface and looking at oscillations of the sun's surface. And from that, we figured out that there are motions in the interior of the sun that generate magnetic fields. And those magnetic fields pop up to the surface. When they're very strong, they actually suppress the convection and they form sunspots. And we'll talk a little bit more about that later. As you go further out to the atmosphere, you get a region called the chromosphere. So the surface is called the photosphere. Then you get the chromosphere, which is the kind of crinkly stuff that you see everywhere here. And then further out, you get the very hot corona. So one of the big puzzles that we try to understand is why the surface is cooler than the atmosphere. And that's something I'm going to talk about. It's one of the mysteries that we're trying to understand. So here's our boring image again of the surface of the sun. It's about 6,000 degrees. The core is 15 million degrees Kelvin. So that's about ×2 to get to Fahrenheit. We've talked about the kinds of measurements that we can take, the different parts of the electromagnetic spectrum. You can see that illustrated here. In the last 3 decades, we've been able to launch satellites into space that allow us to look at all these different wavelengths. And so this is one image of the sun, but really looked at, or one snapshot of the sun, but looked at in all these different wavelengths, from visible to the ultraviolet, to the extreme ultraviolet, to the X-rays. So all very energetic. And as you can see, the sun looks very different in all of these different wavelengths. We see very different structuring, and we're actually seeing very different layers of the sun. I'll point out one thing here. There are some sunspots right here. You can see them right there. There's the sunspots. But if you look in ultraviolet light, you don't see any sunspots anymore. You actually see almost loop-like structures. This is all related to the sun's magnetic field, which drives much of what we see in this atmosphere. So let's take a quick walk through these different layers. Here's the chromosphere in the ultraviolet, taken with AIA, this atmospheric imaging assembly on the Solar Dynamics Observatory that was built at our lab and launched in 2010. And as you can see, the sun now has a lot more features in it. There's regions that are bright, and there's regions that are, here are the bright regions, this one here, and then most of it is less bright and less hot, actually. And it's all related to the sun's magnetic field. So we have a way of measuring the sun's magnetic field remotely. And we do this by looking at the properties of the light, in particular the polarization of the light. We don't have spacecraft flying to the surface of the sun and measuring the field there. That's just not feasible. I know there is a satellite called Parker Solar Probe that has, NASA said, has touched the sun's atmosphere, but it's way out there. It's 8 solar radii away, so it's not even, it wouldn't even fly anywhere in this field of view. So the way we diagnose the conditions of the sun is by measuring the properties of its light, and in particular here, the polarization of the light. And we look also at the broadening of the spectral lines, which I'll come back to. And what you can see here is we see these regions that are very bright in the chromosphere, very hot. They are all locations where the sun's magnetic field is strong, where it's either the south pole, like one polarity, or the other pole, the north pole. The sun and the south and north pole actually don't show much field here at this particular time. That changes because the sun's magnetic field is nowhere near as stable as that of the Earth. It changes on an 11-year time scale and goes through a period of maximum activity where a lot of these magnetic fields poke through the surface to periods where it's very flat and doesn't show much at all. Now if we go further out in the atmosphere, we start seeing gases that are 100,000 degrees. So we're further away from the source of all the energy, and yet we're getting hotter and hotter. And this is very counterintuitive. It's not what you would expect. If you hold your hands close to a candle, it's going to be really hot. If you go further away, it's going to be much more comfortable and cooler. The sun doesn't behave that way, and that's counterintuitive, and that's what we call the coronal heating problem or mystery. The corona is the sun's outer atmosphere. It's millions of degrees. The surface is 6,000 degrees. And one of the things that we try to understand is why this is happening. Here is gas of about 1 million degrees, and here you can start seeing these loop-like structures everywhere. And those essentially following the magnetic field lines. It's because the gas there is electrically charged. It's been ionized. It's been stripped away. Some of the electrons that orbit the atoms have been stripped away, and electrical particles have to follow Maxwell's laws. They have to follow the direction of the magnetic field. And here's the hottest parts of the corona at about 10 million degrees. And actually one thing you can see here, there's a flare going on here. A flare is a sudden release of energy that heats up the atmosphere to even hotter temperatures than we normally see. So here in a nutshell is a curve or a plot that shows this problem. So we're starting at the core on this axis here. This is the distance from the core. The surface is right around here. The center of the sun is here. And this plots the temperature. So we start at 50 million degrees, gradually goes down to 4,000, 5,000, and then we take just a few steps above the surface again, a couple of thousand kilometers. The sun's diameter is about 695,000 kilometers. So just a couple of thousand kilometers more and we get to millions of degrees again. And when there's a flare, it actually goes up to 10, 15, even hotter. Now, a big part of that explanation has to do with the sun's density. As I said, it's a gas, and gas can be very dense or can be very much less dense. And you can see in this plot here, that as you go from the surface, the photosphere, to the corona, the density just drops down very, very quickly. And of course, if you don't have dense gas, it's easier to heat it, and that's part of the solution, but there's more to it than that. So let's take a look at a few movies and show you, I want to show you how dynamic the sun's atmosphere is. So we've talked about the coronal heating, and we see these very linear-like structures. In this case, we see a visitor. This is a planet, and I'm curious if anybody knows which planet that is. Oops, to the wrong direction. We'll come back to it in a second here. Any guesses which planet we just saw? Sorry? I think in this case it was Venus. But Mercury is a very good guess, because Mercury actually we've seen a couple of transits here. And as you can see, that's about the size of the Earth, so very, very small. Here you start seeing more interesting phenomena. This is a coronal mass ejection. This is where the magnetic field of the sun becomes unstable and erupts, essentially. It becomes destabilized. Similarly here, you see some very nice coronal loops that are millions of degrees, but there's also this very dynamic part of the atmosphere, and we try to understand why these things happen. Here, the sun gets a giant eruption as well. It's actually kind of failing. It doesn't make it all the way out into space. Most of it falls back down. And at the same time, you have similar dynamics on much smaller scales here as well. You get strange gases that are just hanging out in places they shouldn't be hanging out. Here you have a giant eruption, and you see kind of a burning prairie grass that spreads over the surface of the sun. And you see loops forming in the aftermath. This is essentially a flare and a coronal mass ejection happening at the same time. Similarly here, a giant eruption. These are not very uncommon. These happen all the time when the sun is active, when it has a maximum in its activity cycle, which is right about now, actually. This year has been a very active time. Similarly here, you see a solar flare. You see how the whole atmosphere around it, in fact, the whole hemisphere actually gets affected by it. And much of it is driven by these phenomena here. This is a bunch of sunspots that are regions where the sun's magnetic field is so strong that it suppresses the convective motions from the interior and suppresses the heat flux coming in from the interior to the surface. Now it has that effect of cooling the gas to 3,000 degrees or so at the surface, but above in the atmosphere it has an opposite effect. Now why do we care about this? We care about it because this is actually you see a lot of things here. It's the hairy sun, we call it. You have the sun's magnetic field on the background, kind of painted on top of the surface of the sun. The green, red, and white lines are regions, magnetic field lines, essentially. We have a numerical model where we've put a lot of equations into a model and then ran it on supercomputers like the Pleiades and NASA Ames and Mountain View. And then the red lines are essentially a region that's become unstable, and that leads to an eruption of these magnetic field lines. Now when that happens, it not only looks pretty here in this numerical simulation, it does more than that. This is another numerical simulation, an illustration of what happens. The sun is on the left. We're now following that eruption, that coronal mass ejection, all the way to Earth. Earth is in that box here, And as you see that as this storm interacts with the Earth's magnetic field, it actually leads to strong effects in the neighborhood, in the near space environment of Earth, in what we call the magnetosphere of the Earth. And that can lead to all kinds of fun around the Earth. And that's illustrated in this. This is the stream of charged particles that the sun continuously emits that we're seeing. We're seeing the Earth in the middle of it. And at some point, a coronal mass ejection goes off. And when that happens, we're going to start seeing the intensity of these particles gets much stronger. You can also see that these particles are deflected around the Earth, and that has to do with the Earth's magnetic field. It forms a shield for us. You can see it drawn here now. That allows us to escape most of the effects of these, but not all of the effects. There's a few weak spots, in particular, where the Earth's magnetic field goes to the surface, like at the poles. Those magnetic particles, those electric particles that come from the sun, can actually make it all the way to the Earth's upper atmosphere. And when that happens, we get northern lights. And that's the prettiest effect of what we call space weather. I'm sure many of you have seen some of the northern lights that have occurred in the last few years. These are now very common because the sun is so active. But there are many other effects of space weather on Earth. And 100 years ago, we wouldn't have worried about them so much. But nowadays we do worry about them because we have a high-tech society that has invented all of these wonderful technologies that are based on electricity, on satellites, on global positioning systems, on power grids, on communications, and all of those things can be affected by space weather and by the sun's eruptions and flares. We can have increased densities in the Earth's upper atmosphere, and that can lead to more atmospheric drag and lead to satellites re-entering prematurely. We have astronauts that we send into space that can be affected negatively by the radiation that comes from the sun and the high energy particles that come from the sun. We have satellites that fly in space where charged particles, very energetic particles, have been accelerated to very high energies in the sun's atmosphere during these eruptions, can hit the electronics on our satellites, and that can lead to the malfunctioning of satellites. And that is, in fact, one of the reasons why I work for Lockheed Martin and why Lockheed Martin has a solar astrophysics lab. When Lockheed Martin, back then it was Lockheed, in the 1960s was building spy satellites to look at the Soviets and what they were up to in Russia, they built the Corona satellites, and they were ones that were taken, one of the earliest technologies that were taking all the spy satellite pictures. And they realized that many of their satellites didn't last very long. And they started investigating why that was, and realized that they were related to particles coming from the sun. And so there was a whole field of research that really opened up in the beginning of the space age to study what the sun really does to the near-Earth space environment. And as time went on, that lab essentially, we don't work on any of the defense-related topics that Lockheed has as its bread and butter, but we have become essentially a lab that mostly works for NASA and NOAA to study space weather and to research the effects the sun can have on our society. And more general astrophysical knowledge. The JWST NIRCam instrument that kind of makes that whole spacecraft work was built also at the lab that I work at. So there's other effects from space weather. There's communications that are disturbed when there's a solar storm happening. There's giant currents that run in electric space, electric currents that run in space that can induce currents on our power grid on Earth and can blow up transformers. So there's a variety of things, and this is one of the reasons why we study the sun. Of course, as NASA wants to go back to the moon and potentially at some point Mars, it behooves them to figure out, how the sun impacts the safety of the astronauts. A couple of years ago, just 3 years ago, I think, Elon Musk lost about 50 satellites because they launched on the wrong day. They launched on the day when the sun had a storm. That led to increased density of the Earth's upper atmosphere. And these satellites, these Starlink satellites, that are they're launched initially in a pretty low Earth orbit before they get kicked up into a higher orbit, where they then do the communications. So they launched on the wrong day, and these things just re-entered within a couple of days. I think lost about 50 satellites. Not a mistake they'll probably likely make again, but nevertheless, there's a lot of new space industry, in part because of SpaceX's advances in lowering the costs of satellite launches. And a lot of people are learning those lessons, especially now as the sun has become very active. So that's kind of the intro to the sun. What I would like to talk about the rest of my time is how we study the physical processes in the sun's lower atmosphere. Why are we seeing all of these very complex phenomena, and how do we study them? And I want to just give you some overview of some of the recent advances we've had in the last 10 years or so, to give you an idea of the progress we're making and the unanswered questions that we're still trying to answer. So I've already talked a little bit about the electromagnetic spectrum, and it's kind of illustrated a little bit here in this combination of an image of the chromosphere and an image of the corona, the multicolored image. And what's illustrated here is the rainbow of light that we get, and the visible light. And all of these little dark lines here are what we call spectral lines. And I'm sure some of you know all about spectroscopy. And I want to talk a little bit more about this in a general sense so that everybody kind of understands how we can diagnose remotely the conditions of the gases in the sun's atmosphere if we can't fly through them. We essentially use the properties of these spectral lines. These are kind of like the fingerprints of the elements that are in the sun's atmosphere, and they can tell us how hot the gas is that emits the light, how dense the gas is, how abundant it is, in the sense that there's different chemical elements in the sun's atmosphere, and we want to understand which elements form where, or are concentrated where. We can even measure things like the velocity of the light. And we do that by measuring the wavelength, the exact position of the light as we disperse it into its different colors. With dispersion, I mean that we're splitting the light up into its constituent colors, the rainbow of colors. We do spectroscopy. We look at light of different wavelengths, and we try to understand which wavelength it's detected at. And one of the main effects that we studied is that we use to determine how fast gases flow in the sun's atmosphere is the Doppler effect, which is kind of illustrated here. If you have a source that's moving in this direction, it's emitting light. You see the waves here. And as the observer sits here, it'll see a shorter wavelength. It'll see blue shift of spectral lines. So the spectral lines will be shifted towards the blue if they're coming towards you, and the back observer will see it move away from him or her, and it will be more red shifted. And so by measuring the properties of these spectral lines, these black lines that are formed by specific elements, like hydrogen or iron or magnesium or sodium, we know what the wavelengths are when the gas is at rest. We can do that in a laboratory here on Earth. And then we can go and look at each location in the sun's atmosphere. Is that light shifted towards the blue or to the red? And we can figure out what kind of velocities are involved. So one of the satellites that I spend a lot of my time on the last 12 years now is called IRIS. And this is the launch of IRIS. It was actually visible from Monterey. It was launched from Vandenberg Air Force Base underneath the belly of a Lockheed 1011 plane. It was with a Pegasus rocket. And I thought I had a movie of this. There you go.
And ignition of the Pegasus rocket.
So this was a very long 10 seconds when that rocket is dropped from the plane, and you hope it turns on. And it did, fortunately. This is actually footage taken from a chaser plane. It's like a military plane, I think. You could see it very beautifully in the sky on the Monterey coast. And the beautiful thing was also, as amateur astronomers, you'll enjoy this, it was launched right around sunset. And after the sun had set, you could still see, the sun was gone, but you could still see in the sky the exhaust, and it had beautiful colors because the sun was still illuminating essentially the plumes of gas tens of kilometers above us, and it went on for hours. It was really beautiful. So when IRIS was launched, that's the third stage, disconnecting here. IRIS was launched in an orbit that's sun synchronous. It looks at the sun 8 months of the year without any interruption, and then it has a couple of months of eclipses. It goes over the poles, and after a while, after the first 10, 15, 20 minutes, it opens the solar panels, and we can start getting power from the sun. It has no propulsion on board, so it just it's been there for 12 years. It's stable, purely based on the energy it gets from the sun, the Earth's magnetic field, and some reaction wheels that are in there. And if you have questions about it, I'm happy to answer them at the end. It's an interesting mystery because it has no propulsion, but it can stabilize its pointing for the last 12 years down to a tenth of an arcsecond. So we've been observing the sun in the ultraviolet light ever since then, the far ultraviolet light and the near ultraviolet light. So these are wavelengths of about 1300 angstroms and another set of wavelengths around 2800 angstroms. And it resolves details as small as a couple hundred miles in the atmosphere. The previous movies that you've seen are mostly with AIA, and that is somewhat lower resolution, but of course captures the whole sun. IRIS only captures a small part of the sun. It's a telescope, but it really acts kind of like a microscope in some sense. So you can see the solar panels here. You see the main telescope tube. It's pretty small. It's only about 8 inches in diameter. So you guys probably have telescopes that are bigger than this. But of course, this one flies in space and can look at light that we can't see from the Earth. And that's why the reasons we put it up in space. And this light that we're studying all comes from the chromosphere and the transition region of the sun. So these are regions that are cooler. They're sandwiched in between the surface and the corona, but they're very dense and actually heating the chromosphere, because the chromosphere is a little bit hotter than the surface, about 10,000 degrees, and the surface is about 5,000. Since the chromosphere gas is so dense, it requires more energy to be heated from 5 to 10,000 degrees than from 10,000 to 1,000,000 degrees, because the coronal gas is so idle, it doesn't have much density in it. So what you can do with an imager and a spectrograph like this is, well, you can do spectroscopy. And what you're seeing here is it's not a full disk instrument, but we are a poor man's full disk instrument. We can do scans. And you can see where the scans don't quite overlap, but we've concocted this image from a scan like this, like a snake going over the surface of the sun. We have 170 different pointings, takes about 18 or 24 hours in this case. But the beauty of it then is that we not only get an image like this, but we get an image for each wavelength. And that allows us to not only look at the intensity, but also at the wavelength. And the wavelength can give us, through the Doppler effect, the flows of the gas. And so this is spectroscopy in action. This is what we love about spectroscopy. Just found this out from my wife recently, who worked at MIT in the past. She's also an astrophysicist. She's in the audience here, and she was saying that one of her advisors said that spectroscopy puts the physics in astrophysics, and that's really true. By diagnosing the properties of the light, through spectroscopy, you really get down to the physics. If you have pretty images, like we did before, you learn a lot too. You learn how things are connected, how things evolve. But what you don't learn is how fast have they moved. Where did these motions initially come from? How hot did things get? How dense was the gas? That you get from spectroscopy. And so here, we make what we call a Dopplergram. So we're essentially, the colors here, the blue is gas that comes towards us at a certain speed, and the red is gas that moves away from us at a certain speed. Now most of this gas gets thrown up and then falls back down, and there's continual dynamics in the sun's atmosphere, and that's what we're looking at here. In this case, we're looking at another planet, and it's actually a different one. This is actually Mercury. And so you can see as it goes across the whole disk that's observed with AIA, we also had a zoom in showing it with the background from IRIS and crossing our slit, actually. The slit is where we get our spectroscopy. And you can see the level of detail that we can resolve with IRIS versus the level of detail we can resolve with the full disk imager. The other thing that's really interesting is AIA is in a geostationary orbit. I'm sorry if I'm getting a little detailed here, but I'm nerding out on this. SDO essentially is an equatorial orbit that sees the motion of the planets almost exactly like we would see it from Earth. But IRIS goes around the Earth all the time, and that's why you get this wobble. You get kind of you can see that it's going down now and going back up. And that comes from the fact that as IRIS was looking at the sun, it was going around the Earth, and what you're actually really seeing here is this motion, is this parallax that you get from having a low Earth orbiting satellite look at the sun in IRIS, and another one is a geostationary orbit. Now, what else did we learn from this? Well, we can diagnose the conditions of the gas in a lot more detail. We can actually walk through a spectral line. So here you see a spectrum. This is one of these spectral lines that was dark in our previous movie. Here it's actually bright in this case. And the movie here is not a movie in time. It's actually just walking through different wavelengths, so making images at different wavelengths. And you can see a very strange change in the features that we see. We start this movie in the photosphere, and as we get closer to this spectral line that's formed in the chromosphere, we see a complete change of the morphology. And this has to do with the fact that at the surface of the sun's gases dominate the magnetic field and concentrate the field into sunspots and into this filigree in the convective downflow lanes. But as we go higher in the atmosphere, into the chromosphere, right around here, we start seeing magnetic field lines dominating the structures. We see sunspots that are cold and dark in the photosphere, but actually become bright as you get to the top of the chromosphere. And so it's starting to give us information about the temperature of the gas, and you can see how much spatial structuring there is here. It's also very dynamic, and we can see that here. With instruments from space, we can follow the sun for weeks on end, for about 3-4 weeks on end, as the features rotate around the sun. Because the sun rotates around its own axis in about 27 days, we can follow it continuously for 27 days, which is not something we can do from the ground. And since we have spectroscopy, we can do it for different wavelengths, which means in this case, different regions on the sun. This is the surface of the sun. This is a couple of 100 kilometers above the surface. This is the chromosphere, a couple of 1,000 kilometers above the surface, and this is the top of the chromosphere. You can see how that morphology changes. So we learn, and you can see also how dynamic the gas is. Continuously, gas is thrown up and falls back down. There's shock waves there. There's heating from magnetic fields colliding, and I'll come back to that in a minute. We also learn a lot about flares and large explosions in the sun. These are a few examples of them. You can see what we call flare ribbons that are formed very rapidly as energy is released in the sun's atmosphere. Mostly energy that's stored when you twist magnetic fields through these convective motions. At some point, these magnetic field lines, they kind of act like rubber bands. They get too much tension in them and they snap, and that's the processes that we see here are related to those kinds of phenomena. When you have spectroscopy, you can look at not only movies like this which show the images, but you also see spectral lines formed here. So now along the dark line that you can't see very well here, but there's a dark line here somewhere where we get spectroscopy. You see all these spectral lines formed, and they have different, they are originating from gases at different temperatures. And they show wiggles, and these wiggles are these Doppler shift effects. These are telling us how fast the gas moves as it erupts. And so it allows us to measure a lot of detailed properties that we can't otherwise. And then there's coronal mass ejections, like these. These are just phenomenal phenomena that we're still trying to understand what triggers them, whether we can predict them properly, because that would really behoove us if we want to understand space weather. With an imager and a spectrograph like IRIS, this is the kind of data you can get. So here we have a movie. It has that black line where we do spectroscopy. And I've shown here 4 different raster steps. So when we want to do spectroscopy of a large field of view, we need to really cross that whole field of view, expose at each position, and kind of make a raster scan, a map of these properties. Once we get these properties, we can then measure the velocities. And you can see the velocities are very significant. They're hundreds of kilometers per second at times for different temperatures. This is 10,000 degrees, 20,000 Fahrenheit, 60,000 Fahrenheit, 200,000 Fahrenheit. So you get multidimensional data. It's what we call hyperspectral imaging, and it gives us a lot of insight into the physics. Here's a failed eruption to kind of wrap up the eruption story. Most of that gas falls back down. And so let's now go back to what heats the atmosphere. There are 2 main mechanisms that people have theorized about for the last 80 years or so, 70 to 80 years. One of them is magnetic waves, and this is really a mechanism, that if you think of these motions that we see here as boiling motions, well, everybody who's boiled water knows that you're not only seeing these bubbles, but you hear something too. You hear sound waves, actually. You hear waves that are being generated. As these turbulent motions are formed, they lead to pressure disturbances, and pressure disturbances are essentially sound waves. In the sun's atmosphere, we get something very similar. We get sound waves, but we get more than that. Because we have this interaction with the magnetic field, all this crinkly stuff, and where regions are dark, these are regions of very strong field, we actually get magnetic waves. And these magnetic waves are very similar to what the kind of waves that you get on a guitar string. Not the waves that you hear when the guitar string reaches your ear, the sound from the guitar string reaches your ear when it's amplified in the guitar, but the waves that are happening on the strings are driven by the tension of the strings. And similarly, the magnetic field has tension in it, and when there's these boiling motions, it creates these waves. And these waves are very powerful waves in the sense that they can propagate for very long distances without being dissipated, without disappearing and depositing their energy into the gases. And so it allows them to travel higher up into the atmosphere and potentially heat the corona. So this is one of the mechanisms that we think might be heating the chromosphere and the corona. Another mechanism has to do with the fact that when you have these magnetic field lines being jostled around by all the motions that you see in the background, it puts tension on the field, and that can lead to reconnection. And we have an image of that here. The interesting thing is we now have numerical models where we put as much physics into our numerical models as possible. These are computer models where we take the basic physics equations of the physics that we think are happening in the sun's interior and atmosphere and run it on supercomputers. And amazingly, they can reproduce convection like this. These are not observations, these are actually simulations. And you can even see the magnetic field lines here, the magnetic field being concentrated in these downflowing lanes, just like we see in the observations. When you compare these models and you observe them as if you had a telescope, so with the same kind of optics and the same wavelengths that you observe with your telescope, and you do a comparison with the real observations, they are a really good match. So the photosphere we understand quite well. The interior we don't understand very well because we don't quite understand how the sun's magnetic field is generated in the interior. That's what we call the dynamo problem. The problem really is also if you go higher up. So we use these Pleiades supercomputer. This is an image taken at NASA Ames in Mountain View. We have these models, and just like in The Martian, a couple of years ago when you saw the movie, and one of the orbital dynamicists went and plugged his laptop into the supercomputers. That's not what we do, but in this movie, of course, in Hollywood, that is what you do. And then once you've plugged in that computer, it says calculations correct. This is, of course, how physics works. Everybody knows that, except in reality, the calculations are often not correct because the models are never perfect. And one of the reasons the models aren't perfect is because we can't really do it, right? If we really wanted to capture all the physics and all the scales that are involved and all the very complex plasma physics, we would need another 300 years of Moore's law of advances in the capabilities of the computers and the chips. Now, Moore's law doesn't apply even anymore in the sense that we've reached our limits there. So we have to make very smart choices about what we do with these numerical models. And making the smart choices is only possible if you have observations to guide you. And that's why in modern science, these two fields kind of go hand in hand and have to march together to make advances. So we go back to the 20th century form of physics, which is the cartoons, which is how it all started, back in the second half of the 20th century. This is the spaghetti model, essentially. Here's the foot points of a coronal loop. We've straightened it out for simplicity's sake, but this is the surface, this is the other part of the surface. And if you now shuffle all the foot points here and here, after a while you get spaghetti. And the spaghetti is not a state that these magnetic field lines like. They will actually try to straighten back out. So when you have magnetic field lines that cross like this, they will try to straighten out and they will actually accelerate gas in that direction and this direction. You get flows in both directions, what we call bidirectional flows. And that can lead to a very sudden release of all that energy that was stored in the magnetic field here and deposited in kinetic energy, mass motion of the gas, and also heating of the gas. So this is one of the main theories for why we think the sun's atmosphere is hot. The other theory, as I said, is the waves. Now, what kind of observational evidence do we have for these models? Well, we have plenty. The challenge now is to figure out which of these models really dominates and in which regions of the sun's atmosphere it dominates. So here's how we construct this model. We have a seed magnetic field at the surface. We see black is one polarity, and white is the other polarity. And then magnetic field lines connect to opposite polarities, like at the other pole. There's no unipoles in nature, there's only bipoles. There's magnetic field lines that don't connect anywhere in our box and go through the edges of the box. And we get electrical currents from these tangled magnetic field lines. And when you look at a movie of that, you can really see how in the numerical model, you see all that magnetic field changing at the surface, just like the movie that I showed in the beginning. The electrical currents are happening all over the place. And they're very dynamic. They occur on timescales a couple of seconds to minutes or hours. And they lead to heating, because we can now go and observe that numerical box and look at it from the side, from the top, and predict what an instrument like IRIS would see, or in this case, AIA would see at the Solar Dynamics Observatory. So we're looking here at extreme ultraviolet light. It's a fake image. It's coming from this computer model, but it looks a lot like what we see in the sun's atmosphere, with dark regions that's cold gas that's being thrown up, with bright regions where heating is happening because of the sun's magnetic field, being jostled around and reconnecting, we call it, magnetic reconnection. You can see another movie of that here. So it looks like we may have solved the problem. The problem is we have another model based on waves that can also create the hot corona. And again, these models are fine-tuned, right? Because we can't get all the physics in. We have to choose the right physics. And the devil's in the details. So we have to go and compare them to the observations. And so one of the things that we did recently in the last few years was that we predicted that these electrical currents would look the same in the chromosphere and in the low corona. These are regions that are in the first few thousand kilometers above the surface. And we got a chance to study that with IRIS. And we can make maps from our IRIS spectra. This is an image of IRIS. From that, we can now, with machine learning techniques, calculate what the densities were in a way that is 6-7 orders of magnitude faster than we would have done it 10 years ago. And so the advances of machine learning there are very, very significant. But we also have measurements of the corona that we need at very high resolution. And we got those from a sounding rocket. I can't remember if this is a movie. I have a movie of this, but I don't have it with me. Anyway, this is a sounding rocket that was launched from White Sands in New Mexico. Flies only about 5 minutes. It gets to 600-kilometer height, and then measures, takes data at very high spatial resolution that we can't take from the current space satellites that we have. But when we compared the images that we got, and it's a movie here actually, the images that we got from the corona with those of Iris from the chromosphere, we found that they actually looked exactly like what we would have expected from the numerical models. So it suggests that in some regions on the sun, in particular regions like this where the sun is very strong, the sun's magnetic field is very strong, it's an active region, we are seeing the effects of currents heating the plasma. I'm not going to go into the details here. The question that we then have is, okay, the chromosphere is interesting, and it looks like some regions of the chromosphere can be heated by these electrical currents. Can they also do it in the corona and the hotter parts of the atmosphere? Well, we don't have instruments that can do that at very high resolution yet in space, but we do have one, IRIS, that can measure cold gas in the corona, and it started detecting what we call nanojets. These are these features that you have the magnetic field lines here, but where the arrows were earlier, and I think I'll have to play the movie again, we actually see little jets, little fountains of gas that are going in the direction perpendicular to the field. And we think, and I'll show you here in a second, what they look like. There, this thing here, these striations that you see, very short-lived, are happening a lot in a region. It's a cool region, but it's in the coronal volume, so all of this is surrounded by very hot plasma. And we see signatures of events that we actually predict should happen if the braiding of the magnetic field lines, the currents of the field lines, are causing the heating of the corona. In particular, we have a numerical simulation here that shows two sets of magnetic field lines interacting. They have different colors here. And when they cross over, they actually lead to very strong flows in the direction perpendicular to the field. So we have numerical models that seem to be able to explain what we see in the data. What we don't know is if the gases are heated to millions of degrees. And that is a question. You can see that here illustrated. So initially the field lines are crossing, and after a while they have relaxed. They're no longer tangled up. The spaghetti has become straightened again. And in the process, gases have been heated to very high temperatures. But what we'd like to know is, does this process happen all over the place, or were these just a few random cases that are not very important? The reason why we want to know that is because there is this other model that also can produce heating of the sun's atmosphere. It's based on these magnetic waves, and so the first question is, have we seen these waves? Well, we see them in the numerical models. This is actually a numerical model of the sun's atmosphere, where we see magnetic field lines in red. They're connecting here, but then there's some that go out into space, and you can see them dancing around. And these dancing field lines, these are the magnetic waves that I'm talking about. These are the guitar string waves. So there are waves in these models. We don't know yet in the models if they are playing a key role in the heating, because we don't capture all the scales that we need to capture to understand that, the very small spatial scales. The problem with these models is it takes them millions of CPU hours to calculate just 1 hour in the time in the life of the sun for just a small box on the sun. And even then we've had to make assumptions, and we can't resolve the smallest details. But some of these waves are generated on very small scales, we think, based on the observations, and those scales are hard to capture with these models. This is another model, a spaghetti model, that also leads to heating of the gas. So have we seen them? We've seen them in observations, yeah. This is a paper that we published a while ago where we see the same dancing motions. You can see them kind of shaking back and forth. We think these waves drive much of the solar wind, this stream of charged particles that continuously erupts, not erupts, but is streaming away from the sun. We now see with Parker Solar Probe, we actually see evidence of these waves further out, and they do a lot of the heavy lifting of heating that gas. So there are multiple mechanisms. The part that's missing, and we see traces of it in the lower atmosphere where we have these high resolution instruments that can look at the cool plasma. What we don't yet have is an instrument that can look at the hot parts of the corona at the same spatial scales, the same small details that can be resolved. I'll skip this one. We've actually even seen evidence for not just the waves, but even for how they're dissipated, for how they heat the gas. And we have models for that, and I'm not going to go into the details of it, but you can kind of see one of these dancing eruptions here. You can see a model of it here. You can see the motions of it. And as this shaking happens, the waves start to get dissipated and deform the tube, this flux tube, this cylindrical tube that we have, and it leads to increases of the temperature. So the real question is, what about the corona? We've seen it in all this cold plasma, and for the corona, we hope to launch in a couple of years, in 2 years, actually less than 2 years now, this new mission that I'm leading, the Multi-Slit Solar Explorer. So we're building this for NASA. It's going to have 2 telescopes, one that looks at images of the sun in extreme ultraviolet light, and one that looks at spectra. And the spectra are very special from this instrument. As I mentioned before, we had that black line in the data that I showed earlier, where we got the spectroscopy, where we really get to the physics. The problem with that black line is that it takes forever to cross, to scan across a region. So instead of a single slit, is what we call it, we have a multi-slit solar explorer here. We have a spectrograph that has 35 slits that are parallel to each other, and that allows us to go much faster over a region and capture kind of the activity in the act, so to say. So these 2 telescopes will look at in the extreme ultraviolet light that we can't see from Earth. We'll have a very similar spacecraft as IRIS. We'll be in a very similar orbit around Earth, so we don't fly closer to the sun. It just means that we have to build very good optics. Actually, our mirrors, in part, are coming from a company in Richmond here in California. Amazing mirrors, very, very smooth, which we need for extreme ultraviolet light, and also very good figure, so that we can resolve details as small as 1/3 of an arcsecond. So we'll have essentially an instrument like IRIS, but for the corona, and it'll be better than IRIS because we'll have much better spectroscopy. So the kind of data we'll get from it will allow us to capture not just images like these 2 here, just for a part of the sun, not the full sun, and then along these 35/7 slits, we get spectroscopy at different temperatures, different spectral lines. And we'll be able to scan this whole region in 12 seconds instead of in 10 minutes. So that's going to make a real difference, because one of the challenges is, in all of our movies that we've seen before, is that energy is often released on very small scales and very rapidly spreads to very large scales. Capturing that with a spectrograph is hopeless. Of course, with spectroscopy, we get not just the intensity of the light, like in the images, but also the velocity, blue coming towards us, red away from us, and the broadening of the line, which gives us an impression of how turbulent the motions are, another key discriminator between models. To illustrate the difference between MUSE, the name of our new instrument, and what we have with single slit spectrographs, you can see here a simulation of what each of these instruments would do. This is the actual ground truth. This is a numerical model of an eruption. You can see the intensity at about 1 million degrees, and you can see the flows at the same temperature. And you can see how complex this whole process is. But just the images alone is very hard to figure out what's going on. With the flows, we can make a much better idea how this is triggered, these eruptions, and how they evolve and how they impact the surrounding corona. With a single slit spectrograph, it takes forever to build up a map. And while we're building up that map, this whole region has already changed, right? With MUSE, you can actually capture that evolution in a way that we've never been able to capture. And that's the really unique part about it. And that's because we have these 35 parallel slits that allow us to just scan very quickly between these parallel slits to capture the whole scene. You can see another example of that here. In 12 seconds, this is what we get from MUSE. This is the real ground truth. And this is what we would have gotten from a single slit spectrograph. So MUSE will focus on the coronal heating aspects, which I've talked about at length. but also the drivers of space weather. So here you see a numerical simulation of an eruption, and Muse will be able to measure those properties in a way that we haven't been able to do before. We'll be able to measure the Doppler shifts, meaning we'll be able to measure how fast this gas is accelerated towards us in the early stages of the eruptions. And that's really key to predict how fast these coronal mass ejections will get to Earth, something that we're really interested in if we want to predict the impact of these events. And generally, with observations like this and comparisons with numerical models, we have numerical models for how these things are triggered. In this particular case, this is a numerical model with different colors at different temperatures of an eruption. We know exactly what happened in this numerical model, what triggered it, and it had to do with destabilizing the magnetic field. But from the images alone, we can't tell whether this mechanism is at work or any of the three other mechanisms that other modelers have found could lead to these eruptions. But if you go and observe it with Muse-like instruments, you can actually distinguish that because you can do spectroscopy fast enough to see that rapid evolution, and that's what we're going to do with Muse in a couple of years. We have about 100 engineers working on putting Muse together right now, and hope to launch it in the summer of 2027. I'll finish my talk with another reason for why we study the sun, and that is that there's pretty strong evidence, not just from from looking at other stars, where we don't see these details, but we can see very large flares, like super flares that are 100 times or even more stronger than what we've seen in the last 100 years on the sun. We know there was the Carrington event in the 19th century where telegraphs were getting electrically charged, and people got electrical shocks from the fact that there was such a huge storm that it led to electric currents being induced onto the telegraph network in the continental United States. We know there's larger events in the historical record, in the archaeological, so not the archaeological, but in the record in ice cores and whatnot, of much larger events. If an event like that, a super flare like that, were to happen, I thought this was a movie, there we go. This is just an illustration from some documentary. But if an event like that were to happen, we're looking at 6 to 9 months of no power in the continental United States and economical loss of trillions of dollars. And this is not a scare story here, but I think it's a reality. We've never encountered such an event during our pretty short time of being a high-tech society, but it behooves us to understand how often these occur and how we could mitigate against them. Another reason to study this, of course, is because we now have discovered lots of exoplanets, planets around other stars, like in this cartoon here. And we know these exoplanets are often orbiting stars similar to the sun, or stars that undergo flares and coronal mass ejections. Some of that ionizing radiation from these stars can strip exoplanets from their atmospheres. And people are now trying to predict the habitability of exoplanets, and understanding how space weather on the sun works and how it impacts Earth. Eventually, if we get better models for how that works, we can extrapolate that more easily to other environments like other stars. And with that, I think I'll thank you for your attention and happy to answer
questions.
Yeah, hi. Some follow-up questions on coronal mass ejections. Do they happen evenly, so to speak, evenly distributed around the entire surface of the sun, or more at the poles, more at the equator, more at sunspots?
There's a concentration around what we call active regions, so around sunspots, or they're often formed because between opposite polarities we have what we call a neutral line, where the black and white kind of touch, and there are often filaments that are formed there, cold gas that is formed in a region that is relatively unstable, and they're often formed there. But we get them from the poles as well. There's what we call a crowned filament that goes around the poles that often gets destabilized. Some of my colleagues at Lockheed have found that there are events that are sympathetic, as in something happens here on the sun, and a couple of minutes later it propagates. I didn't have a movie of that here, but you can actually see these disturbances propagate over the whole atmosphere of the sun, and a couple of minutes later they can destabilize conditions half a solar radius away and pop something else off there. And we think that there's also what's just happening on the background of the sun, sorry, on the backside of the sun, the side that we can't see, that can influence the front side. So what we really would like in the next 10 years is a constellation of instruments that can look at us 4π. You know, if we want to understand weather on the Earth, we couldn't really do that until we had measurements from the whole hemisphere. We have things like jet streams and all those kinds of effects. We want to understand something similar. We get data like that for the sun as well. But they happen predominantly in these active regions. There's a lot less of them during solar minima when the sun is not so active, but there still are quite a few, just not as spectacular.
And I know this, the answer to this question will depend upon the size of the ejection, but roughly speaking, given that it could occur anywhere on the sun's surface, what are the odds, like what percentage are of a trajectory that would hit Earth compared to just going out in space?
It depends on if you look at the whole hemisphere or like the full 4π of the backside and the front side, but the geo-effective ones are on the front side, but not on the leading side, but more on the trailing side, and that's because of the Parker spiral. It's the way the magnetic field of the sun dances around and it's kind of like a ballerina skirt that goes around the sun. They propagate from that direction more. And so there's the geo-effective one, we call them. Those are the ones that are more on the center of the disk and then the trailing side.
Last on this subject, have you seen any ejections that are what we estimate to have been Carrington event size that have not hit Earth so that you can study those?
I don't think it was Carrington size event, but there were some very big ones that we missed in the last 5 years that we were just lucky. But nothing Carrington size to my knowledge.
Thank you.
Is there much understanding of what physical mechanisms set this 11-year cycle for the sunspots?
There are various theories for it, and most of them have to do with the interface between the radiative zone and the convection zone, and the fact that there's differential rotation there. And when I talk about differential rotation, I mean that the rotation speed of the sun depends on the depth that as you go into the sun. And if you have different rotations at different depths, you can actually stretch magnetic field lines and generate currents that way, and that can generate magnetic field. Part of the cycle, and I didn't go into this here at all, because it's a whole other topic that I'm not necessarily a specialist on, has to do also with the way the magnetic field gets transported from the interior to the surface, and then at the surface actually migrates towards the poles. At the poles, then gets pulled back in, and then there's a pole to equator shift as well, or flow, a meridional flow, that brings magnetic field around. And the thought is that this forms a cycle that naturally recurs. It's a very chaotic cycle. There's been periods of time, as you may know, where the sun is not very active at all, where the sun's magnetic field seems to have gone very quiet for a couple of decades. It was called the Maunder minimum, where it was actually more than a couple of decades where there were almost no sunspots. You know, Galileo discovered sunspots, and then they were gone for like 100 years, and then they came back. We've seen evidence in the historical record on Earth that suggests that these periods occur, you know, chaotically, but they occur regularly. And so there's a huge discussion in the field still, probably about 15 different models on making predictions for the next solar cycle and how strong it will be and when it will peak, and they're all over the place. So it's very much an active area. A big part of our understanding there depends on measurements of very small flows in the interior of the sun, and that is its own field called helioseismology, where just like seismologists on the Earth can figure out something about the interior of the Earth through looking at the surface waves, could do something similar on the sun. And people are studying that in great detail with instruments like SDO as well, another instrument that we built at Lockheed. And there's still a lot of advances that need to be made there. It's a general problem. We learn also from looking at other stars, because other stars also show activity cycles, and the rotation rate of the star has a big role to play in this, because it has to do with this differential rotation. But the dynamo problem is mathematically very difficult to track, to do properly, to capture all the scales and all the time scales involved, because it goes over many, many years or hundreds of years. So it's an active area of research. I think electrical power systems, the idea there would be to make sure that your loads are reasonable at that time. A lot of the problems stem from transformers blowing up. And this is also an active area of research in the sense that when my colleagues tried to study this in the last 10, 15 years, they couldn't get any data from the power companies because the power companies don't want to give it out. They don't want to show that they're vulnerable. And my colleague actually ended up talking to a Swiss insurance agency that specializes in insuring electrical power companies and found evidence for a 27-day cycle in claims that was related to the solar cycle, the solar rotation and activity on the sun. So his guess was a couple $2 billion a year for sure are caused by natural effects from the sun, but it's hard to for the power grid people, they don't necessarily know this, right? They just see, oh, a transformer blew up. So in terms of mitigation, that would be one of the things, like just understanding better how sensitive your equipment is and making sure your loads are reasonable, I guess, if you get an event like this. Communication-wise, there's the apocryphal story. It's not apocryphal. I think it's a real story now that during the Afghan war after 9/11, there were soldiers that had, in fact, there was a movie made of this, that had communication issues, and they were stuck not getting the help they needed from whatever, the air, and then they were stuck and surrounded, and several people died. At the time in the movie, they complained about these crappy contractors that built these crappy phones, or satellite phones that they used. But as it turns out, people did research on this a couple of years later and found that there was a day of very strong geomagnetic disturbance driven by the sun that disturbed the communications in the ionosphere. So these would be things like if you had some advanced notice, you would, as a military, the military is very interested in space weather. A lot of the funding comes from the military as well for that reason, because they want to understand should there be operational limitations. If you fly over the poles with a plane, if you work in a plane on a regular basis, you do get a higher exposure rate to radiation that way, and so you could avoid not flying over the poles that day and going a little bit lower latitude. So there's a variety of things. In terms of spacecraft, you could put things in safe mode, so you're not actively operating while your bits are flipped. That's essentially what happens. You get bits that are flipped, and then a lot of the cost of electronics in space is radiation hardening and making these kinds of things. So there's a list of things that you could do and you could envision. If you send astronauts to the moon, you want to make sure that you don't send them out when there's a high risk of solar activity. During Apollo 16 and 17, I think, or 15 and 16, there was a very, very large CME that happened. At the time, they weren't aware of this, but if the astronauts had been on the way to the moon during that time, they would have had major radiation damage. So we got lucky in the past, but it doesn't mean we'll stay lucky. And there you could go and surround yourself by your water supply or something, or you put your lead underpants on or whatever.
Thank you.
Yep. There was another question.
Can you talk about just the accuracy in terms of you track an active region, and how often those turn into a mass ejection, or just I don't know how accurate that is, or what level of prediction you have?
Yeah, that's an active area of research. Before I get into that question, I want to give one more example that I was actually surprised by. I went to Congress to lobby a couple of months ago because a lot of the heliophysics science that you see described here is threatened by the president's budget request. The proposal is to cut it by half, essentially, which would lead to a loss of expertise that's been built up over 5-6 decades. But one of the examples that we gave to the congressional staffers is that last year there was a major solar storm, and it led to multiple billions of dollars in agricultural losses. And the reason for that is that, I didn't know this, but a lot of the agricultural planting and harvesting is now done automatically with GPS. And the GPS accuracy just goes down the drain if there's a big solar storm because the ionosphere is disturbed, and it's all about the timing differences between the satellites and the ground. So that's just another example of where if you knew that, you could, essentially they missed their planting season or they missed the harvesting, and so plants rotted or weren't planted in time. So you could envision that you had mitigation for that. Back to your question about active region tracking. There's a lot of machine learning that's going on now. So one of the things that we know, it has to do with the sun's magnetic field. And people do make predictions. I have been making predictions for the last 15 years. And it's a little bit like weather predictions in the 1960s, I imagine, where you know, you say, well, there's a 20% chance of this or a 50% chance of that. And, you know, I grew up in Belgium, it always rains, and so there's a very good chance that if you say it's going to rain tomorrow, you're right. And, you know, so we're kind of at that level, maybe a little bit better than that now. But machine learning is helping us. We have 15 years of data from STO. And actually, one of my colleagues just recently finished work with IBM and NASA, where they built a foundational model where they ingested 9 years of that data into a model that then they can go and figure out, okay, based on all of that data we have, what are the correlations that you see between all these different measurements that can lead to a flare? And the hope is that we get better data that way. I think we're at the level of, you know, yeah, there's a 60% chance of a flare tomorrow, which gives you a lot of uncertainty. And it has to do a lot with the way the magnetic field evolves, but there's also signatures on shorter time scales which would be of interest for things like astronauts and spacecraft that we've discovered with IRIS, actually, that we haven't been able to exploit fully because we don't have a full disk instrument, but where we see the beginnings of magnetic reconnection, where magnetic field lines start to getting snipped at the bottom, and eventually if you snip enough of these, they kind of anchor this whole structure down. If you snip enough of them, eventually it destabilizes and takes off. And so there's hope. We see evidence for this. It's very much at the research level, not at the level of predictions, that if you build other instruments that capture very specific, subtle hints that as a human you can't necessarily detect, but with machine learning you can actually ingest all of that data and figure out where the correlations are. There is hope that in the next 10 years, if you build the right instruments, you can get a much better prediction. Yeah.
Is there a discipline of science that is putting all of the pieces together, like from heliophysics, geophysics, volcanism, rotation of the planet? So how is science dealing with sort of coordinating all of these different disciplines to get a general idea of, like, you move one, it's going to change another?
It's a challenge. I think even within the field of heliophysics, it's really formed of 4 disciplines. There's solar physics, which is what I'm focusing on. There's heliospheric physics, which is really the solar wind, which is the region of particles that, as it's left the atmosphere of the sun, that bathes through the whole solar system. There's the magnetosphere, which is the largest scale magnetic field environment of the Earth. And then there's what we call the ionosphere and thermosphere, which is the regions of the upper atmosphere of the Earth. And just connecting all of those parts, you need specialized knowledge to be an expert in each of these fields. Connecting these is not straightforward. It's often it's interdisciplinary often, because you need different instrumentations. You need people who are experts in numerical models. You need experts that are in theory or in machine learning and in observations. Getting that together is a challenge, in part because the funding is not set up that way typically. It's often science gets put into little blocks. Volcanology, that's its own field, and we do have the American Geophysical Union conferences here in San Francisco in December every year. Tens of thousands of nerds in town then. And it's not every year anymore. It used to be every year, but it's every 2 or 3 years now. It's in the Moscone Center, and there all of these disciplines come together actually. And there are sessions there to do interdisciplinary stuff, but I would say part of it is like there's different time scales involved. So volcanology and climate studies and solar have a connection, because in the late 20th century there was an active discussion on, are we changing climate with Earth, with human-made emissions, or is it just part of the natural cycle of the sun? Because the sun's solar activity cycle does lead to changes in what we call the irradiance of the sun, the total radiation that we get from the sun, on an 11-year cycle. But there's secular changes in there too, that are not just periodic. And so for the longest time there was a discussion of that. That's now been settled, and so we now know humans are doing this. But so there are interfaces there. It's not perfect.
All right. Thank you very much.
Thank you so much.
We so much appreciate you coming out.
Thank you for the invitation. It was a pleasure.
And next month, our lecture will be regional astrophotographer Gary Lopez on the art of astrophotography. So hopefully see you again next month.
All right.